All right, welcome back. So in this presentation, I'm going to talk about cache misses and you're going to see when you do an activity after this, how you can actually empirically discover how many misses a particular piece of code has in it. So let's start by thinking about um, a very small simulation. So we're just going to look at what happens when our code accesses memory in a particular order. And we're going to do this by starting out with a cache where e equals 1. So we only have one line per set. This is also called a direct map cache. So this is a really miniature example right now, just so you can think through um, what's happening as our program is accessing um, pieces of data, whether it be data elements or possibly instructions from your program. And so we're going to start here with a ridiculously small amount of memory, 16 bytes total. And this is just so we can get a sense at a real low level what's going on. And suppose that we have a cache over here that has a total of 4 sets. And in it, we'll have these things that I've talked about before, the valid bit, a tag, and then the data itself from our main memory over here is stored in the line in the cache. And there's only one line per set, you see here. So 16 bytes of memory, only 2 blocks in a byte, and a total of 4 sets. And then our E equals 1, or direct mapped caching. So let's think again about how we refer to an address in this tiny little example. So we're going to need, we have 16 bytes here. And there's 2 bytes that can fit in a line of cache over here. And so every 2 bytes of main memory maps to a set. And so we have 4 sets total, so the first 2 bytes map to set 0, the next 2 bytes map to set 1, the next 2 bytes map to set 2, next map to set 3. And then we have to start over again. So all of these constitute, this first half of our memory constitutes our tag 0. And then we start over again with set 0, set 1, set 2, set 3, mapping the next 16, or excuse me, the next 8 bytes of our memory. And so each of these now belongs to tag 1. And because we have such a small amount, that's all we have. And so in this particular case, our tag is either 0 or 1. So we only need 1 bit for a tag here. This is a very silly, tiny example. And then since we have a total of 4 sets, we need 2 bits to represent the set, because the highest one would be 3, which is 1, 1. And then we only have 2 bytes in a line over here, 2 bytes that map to a particular set. And so it's either byte 0 or byte 1 of the particular line that can be stored in there. And so we only need 1 bit in this case to refer to the 2 bytes that are stored in a particular cache line. So this is our mapping. This is our, for this really tiny example, how we map the cache to our small amount of memory. Okay, so let's do an example. So what is the cache address for address 12 over here in memory now? So if we want to figure out what the cache address is for this, well, this is now in set 2, tag 1. So if we are to fill in our address using our notation of tag first, then set, then the byte offset, it goes into tag 1, which is this one here, the set 2, and in your book these are called CT, CI, and CO. So for the tag, the set index, and then the offset into the set. Now, this offset being 0 in this case is because the byte 12 of memory is in the 0th position in the line that it maps to in set 2. So this would be the address in binary. 1 for tag 1, 10 for set 2, and then byte 0 here as the offset. So that's the way we would address memory in this small example. So now let's suppose up here in the orange box that what we have is a program that's running. And it is addressing particular places in memory that have been translated into these addresses that we just talked about. So the underlined part here is for the set, the first bit here is for the tag, and then the last bit here is for the byte offset. So here are the different addresses in memory that are being executed in the program at any particular time, and we're reading 1 byte at a time in this case. And so to start off with, we're going to read in, we want to read byte 0 over here. Well, that's set 0, tag 0, offset 0, right? And that you can see from right here. And so in that case, when we read that, that's a miss because right now we have nothing in the cache. Okay, so we're just starting out in our program here. And so that's a cache miss. And so what's going to happen is that'll get read in. The valid bit will become 1. And here we know now that we have set 0, tag 0 in there. And both block 0 and 1 got read in. And so then if we next want to read byte 1 from the block here, then that is a hit because it already has been brought into cache. Now let's suppose the program skips a little bit and wants to go down here to byte 7 and read that. Well, that's in, that corresponds to set 3, tag 0, and offset 1. It's the, this is the 0th and this is the 1 byte of that, for that byte of data. And so of course that, since it maps to set 3 down here, that is not in cache, and so that'll have a miss. And then if we next want to access byte 8, Well, that also is now a miss because that maps to set 0, but tag 1 here, right? This is tag 1, so set 0, tag 1. And so right now, the set 0 contains tag 0, so that's going to generate a miss. And so that'll be a miss, and and what'll have to happen is that this this 2 bytes will now have to replace what was in there, and you see the tag changes. And so now if our program were then to access the byte 0 again for some reason, we would have a problem because we just got rid of it, and we would generate yet another miss and have to bring the other one back in. So hopefully you can see why it's awfully nice to, instead of this direct map caching, to actually add these extra lines in each cache set, because when we do that, something like this last case wouldn't occur, and we would have ended up being able to have both of these in there, and this one would have resulted then in a hit. So it's usually in modern systems we use these E-way cache setups so that we can avoid some misses that might occur like this. Okay, and now these misses are very costly. A hit means that the data is accessed faster because we can get it right from cache. Okay, but a miss from cache means a much longer time because we have to go all the way over to memory and get it and bring it back and put it into cache again. And so every time we do one of these loads, if the load can grab the data from cache, we're much better off than if it has to go all the way over to memory and back again. And so what we want to do is to be able to avoid misses as much as possible in our code by making sure that we take advantage of the locality that I spoke of in our previous presentations. So now let's move to a much higher level and think about this in terms of some code that we might have. And now what I'm showing over here on the left is a new cache, which still is direct map, so it's still one line per cache set here, but the lines are bigger, so they're 32 bytes. What that means is if we have a 32-byte line, we could actually hold 4 doubles in it. And in this case, I'm showing that we happen to have 8 sets. Well, what that means in terms of a program like you see over here is if we are accessing a 2D array and we're accessing it in this fashion, you can see the name sum array rows. We are in the inner loop here going through every element in a row before we switch to the next row. And you remember that is good spatial locality. That means we are going to access the first element, the 00th element, and then we're going to access the 01st element. But what happened was that when we access the 00th element, we get a miss. But then you can see that in the first line, let's assume that we were filling up the cache from the beginning with with a A0. So A00 does map to this portion of our cache, the set 0. So for simplicity's sake, let's assume that. And so what happens here is that we have a miss to bring in 0, 0, but then at the other three elements, 0, 1, 0, 2, and 0, 3, are all in this line of cache. And so what we can see now is that we can think about a ratio of hits to misses. The miss to bring it in, and then 3 hits because now it's in cache. And so there's this nice ratio of 3 to 1 in this particular instance with this 32 bytes of 4 doubles. Now, in contrast, if we look at this code here where we're summing along the columns, so we've swapped J and I here in the nested loop, you know from our past presentations and from trying the activity, hopefully where you were timing these, that this code was slower, and we know it's slower because what's happening? It's bringing in 0, 0, but then it needs to bring in 1, 0. And the question is, where is that? It turns out that 1, 0 is going to map down here. And so that in these sets here, we end up getting a whole row in. And then the next row would be in these sets here. And so row 1 is going to be mapped down here. So 1, 0, first 0, 0 would be accessed, and then we'd access 1, 0 here. And then when we want to access 2, 0, we'd go back up over here. We'd have yet another miss because we'd have to throw out what was here and put it back in here. So you can see I've contrived a fairly kind of worst case scenario of what could happen here. But this is kind of exactly the sort of thing that we end up seeing when we go column-wise instead of row-wise with these 2D arrays. And so the ratio here of hits to misses is 0. We just keep missing every time by going back and forth here. And so it's just a truly untenable, bad situation. And so what you're going to do now is you're actually going to measure in the next activity using a program called Valgrind. You're going to measure exactly how many cache misses and cache hits there are for functions like this. And so this is, I find, really interesting because we can, in fact, ask the system just exactly how many misses and hits any particular program created. So it's a very interesting exercise that I hope you'll find interesting as well. All right, so now let's think about if we were to go from this example where we've got 4 sets that are direct mapping or one way, so we only have a single line here. What would happen if we did consider this improvement of going to K-way or associative cache, which really all of our caches these days are like this? There's a couple things we could do. So we could keep our cache exactly the same size, but have an extra line here. So that's what's showing here. Here's our set 0, but let's have 2 lines in there. And then here's our set 1, and let's have 2 lines in there. Hopefully you can convince yourself that previous set of reads that I had gone through would get just a little bit better. And that was a very small example. Typically, your program does a whole bunch of these, right? And you'll end up saving some misses and end up with some hits by having these extra lines. And now in this particular case, we kept the size of the cache the same. So what that meant was we went down from 4 sets to 2. And what that does mean then is that we've ended up over here with a remapping. So we've only got set 0 and set 1, and then we start over set 0, set 1, set 0, set 1. And so then we'd have more tags here. And of course, the addresses would then change because we need more bits for the tags now. So, so this is one possibility, is to go ahead and keep your cache size the same. But over time, what we've really done is also increase the size of the cache while also going to something like a two-way system. And so if we go to the idea of adding extra lines, then in this case, now if we go ahead and have 4 sets, the total size of our cache has doubled. And so that is often, you know, the evolution that's happened with our CPUs, is that we've gone to this notion of having more cache, and so that the mapping now goes back to what it was in the example that I started out this presentation with. So now the mapping is back to the same as that first one-way case that I said, but now we have double the amount of cache. So the key idea here is that adding extra lines is very likely to decrease cache misses. And in fact, the way that the CPU designers tweak and fine-tune the size of their caches and how many lines they have in each set is by running a whole bunch of representative programs. So benchmarking, if you will, is a term for this. They'll run a whole bunch of programs and then validate that that a certain size of cache and a certain number of lines results in about the fewest amount of misses that they can get, and so that this hit to miss ratio is remains fairly high. Okay, so now let me go back to something that I talked about before, just so you recall how it works. So here I've shown an associative cache where E equals 2. So, and here's all the gory details. And we're saying that the cache block size in this case is 8 bytes. So here's our data that's going to be loaded into the cache. And then, of course, we need the tag, set, and offset bits for any address of this cache. And so if we have a particular address, the first thing we do is get to the right set. And then once we've zeroed in on that particular set, then we look at the tag bits and we compare them. And in fact, this is a pretty fast operation on our machine. And so they can be sort of done as I'm showing here, kind of compare them all at the same time and figure out which one, if any, actually matches. But this is fairly sophisticated hardware, and this is one of the reasons that we haven't gone to much more than 8-way at level 1 cache, because in order to do this simultaneously like this, quickly. We don't want to have too many of these lines. So we compare them, and if there's a match, then it's a hit as long as the valid bit is also set. And then in this particular instance, suppose we were looking for block 100, which is 4, then that's where we would start reading. And there's, maybe we were going to read 2 bytes, and if so, then we'd read those 2 bytes. Now, if there was no match, remember that one line in the set gets selected to be evicted and replaced with the one that we want. And there are a lot of different replacement policies. We could randomly pick which line would get evicted. The least recently used is kind of a gold standard. Most of the time, there is some way of knowing which of these was last used. And it does require actually a little bit of extra bits, because basically there'll be some sort of a counter that will keep incrementing every time one of these lines is accessed. And it's not very long, so it will sort of quickly overflow and go back again, but it's the way of determining which of these was the least recently used. And so that's how the system decides often, is to pick the one with the least accesses recently. Okay, so now also let's just remember about our common Core i7 architecture. The machine that you're working with for class, our server is very similar to this, so it has an instruction cache and it has a data cache at level 1. And, instructions are typically have good spatial and temporal locality. If we happen to, have some kind of weird code where we go way back to some instruction that was executed a long time ago, we could have some temporal locality issues, but generally speaking, you see pretty good spatial and temporal locality from the instructions. And in the data cache, of course, the programmer really has to ensure this good spatial locality. And so the example that we've been looking at, summing the rows or the columns from a 2D array, those are examples of when you do it row-wise, that's good spatial locality, and you can have poor spatial locality. In the next presentation, I'm going to show you even some more interesting examples of this. So the idea here is that in activity 3 now, you will be using a program called Valgrind that's actually lets you see in L1 instruction cache and D1 instruction cache how many cache misses there were. So you get a very good indication of exactly what happens in your program. And so this is a tool that programmers will use sometimes to profile their code to see how well it's working. So I want you to go ahead and try the last activity in the memory activities, and you'll be able to notice the instruction cache and data hits and misses. You're going to empirically collect the data using this Valgrind program, and it's going to report it for data and cache. And so the things that we um, intuitively now understand about spatial locality are really going to show up by empirically collecting data about how many cache misses there were. And so you'll use this tool to be able to do that and see it. So go ahead and give that activity a try. And next time I'm going to show you some even more interesting examples of code and some very classic issues that we run into if we aren't thinking carefully about the locality of our programs.